Hello, I'm Hugh Manfield, and welcome to my science channel. Today I'm going to be talking about more of what Einstein got wrong. Einstein's basic philosophy, which he clung to, was to only consider what he called material bodies. If we have a body here and a body here, and there's a distance s between them, we can't think of the space that they occupy. We can only consider the bodies and the motion relative between them. And the distance between the bodies is a property of the bodies, not space. He didn't even want to consider the concept of space. It's only material particles moving about on some sort of imaginary stage. He shunned dealing with space as anything real. So we can put a coordinate system attached to one of the bodies, and we can attach another coordinate system to another body, and we can set them into relative motion, and we can compare the motions based on these coordinate systems. Now this is what Einstein did with reference frames, but he would never consider an empty reference frame as having any significance. It would just represent space, which to him was imaginary, nothing real, something that you didn't really have to deal with. Space only became real when you attached a coordinate system to a material body. So if we look at the three forms of gravity, we have linear acceleration, curvilinear motion, and standing on a massive body. Any experience of gravity can be broken down into these three components. So if you're designing a roller coaster that sits on the surface of a planet, you can do all your design work by breaking down the type of motion into these three components and creating a complete picture of what you're designing. And since there are only these three ways to experience gravity in the universe, Einstein's attempt to generalize was really unnecessary and misguided. So let's take a look at his 1911 paper. And I've created Stan, an imaginary box that's being pulled through space with a constant force. So Stan feels a constant acceleration. And here I've used the term acceleration. And Einstein called this K prime. It's accelerating through space at a constant rate. And that's something we can analyze with Newton's laws and in a Galilean sense. Then Einstein imagined a homogeneous gravitational field, which we have when we have Ricky in a box sitting in that imaginary field. And she's going to conduct the same experiments that Stan is going to conduct over here. So Stan has two clocks that emit photons and can measure a photon when it's received, a feather, and a hammer. So at some appointed time, t0, the feather and the hammer are released, and they enter into what Einstein called an inertial reference frame, K0. Now this is how, in his paper, he dealt with this situation. And it's essentially correct. And the photon is also a falling object, just as much as the hammer and the feather. So the photon, during the time it travels, the reference frame K accelerates upward, where the photon is in K0. So there's a relative velocity increase, and the photon arrives with greater energy. Okay, so that's all well and good. So then, when Einstein analyzed his theoretical imaginary homogeneous gravitational field, he did the same thing, except he didn't introduce the K0 inertial reference frame. He talked about photon propagating in a gravitational field. Well, this is a fallacy of thinking and something wrong. Photons propagate in a state of free fall. They're just like any other dropped object, like the hammer or the feather. In order to properly analyze the situation, you have to introduce the inertial reference frame K0, at which point you would say that in a gravitational field, inertial reference frames, which are occupied by the hammer and the feather and the photon, so we can attach a material body to that to make Einstein happy, this inertial reference frame will be accelerated through the action of gravity downward relative to the observer in the gravitational field. So it's just like when I release this orange. It's going to enter an inertial reference frame, and that reference frame is going to be drawn down to the surface of the Earth. And there it goes. And if you were riding on that orange, you would feel weightless. You would be in an inertial reference frame, and that's when you feel weightless. So if Einstein had introduced this K0, then he would have been forced to consider that actually the same process is going on in both of these boxes. The inertial reference frame is accelerating downward relative to the observer, who is in an accelerated reference frame. And over here, the inertial reference frame is accelerating downward relative to the observer in the gravitational field, which is an accelerated reference frame. But if Einstein's thinking is correct, and that as long as there's nothing occupying this K0 reference frame, if it's empty, it shouldn't have any effect on the observer. So once the hammer and the feather drop to the floor and the photon is received, any potential K0 reference frame falling by shouldn't have any effect. But gravity goes on and on. So in order to explain why gravity can go on and on, he would have to accept that an empty reference frame must have some significance, and that goes against his entire philosophy, and that's why he could not conceive of what I've done in fluid space theory. But it's undeniable. When you release an object, it goes into an inertial reference frame, and that reference frame is drawn downward. There it goes. And there goes another one. It's undeniable. It's happening constantly. And not just when I'm dropping something, it's happening now. Empty reference frames are falling past in the Earth's gravitational field and causing the sensation of gravity for me. Because the only force acting on me is the force of the floor against my feet. I'm in an accelerated reference frame, which means inertial reference frames are falling past. There goes another one. There goes another one. They're constantly going by. And all you have to do to see it in action is drop an object. So, to illustrate the difference between Einstein's theory of general relativity and fluid space theory, let's take a look at Niagara Falls. Now, let's say that this picture was generated using Einstein's theory of general relativity. You would say, well, that's a pretty good picture. He's captured Niagara Falls pretty well. Well, here's what fluid space theory brings to the table. Check it out. Much better. It gives you a much better understanding because it admits that space is actually flowing. It's not a static, fixed representation. So once again, Einstein's version and fluid space theory version. Fluid space theory brings a more complete understanding of the motions of space-time to the table, and that's what makes it superior. So let's go through each of the different ways to feel gravity, and we'll go through it in detail. We'll start with linear acceleration. Now, with linear acceleration, we can use Newton's laws. The acceleration equals the force divided by the mass. So if we have a constant force and a known mass, we can know the constant acceleration, and we can imagine an acceleration field in the space surrounding Stan in the box. But that won't help us understand the relativistic effects. Over time, the box is going to move faster and faster and faster relative to its starting point. And a clock on board that box will run slower and slower and slower relative to a clock located at the starting point. And in order to understand that, we need to use a vector field. And we can create a vector field basically knowing that the velocity of the box at any time is equal to acceleration times the amount of time that has passed. So we can have an acceleration field and a vector field, and we can understand everything we need to know about the gravity in the box and the effects of relativity based on these two fields. So only special relativity is needed to understand this, and we don't need general relativity to understand what's going on in this situation. Okay, let's take a look at circular motion. Once again, we can define an acceleration field, which is going to act radially out from the center of rotation, and it's going to be equal to the radius times the rotation rate squared. And we can create a variable acceleration field within the space surrounding the rotating disk. Let's say this was a wagon wheel style space station, and we could tell what kind of gravity Ricky would have on any deck and at any position around the loop. So we could tell about the gravity, but what about the relativistic effects? As she gets farther and farther out, she's going to be moving faster, and the clock at the bottom or the outside of the disk is going to run more slowly than one at the center. In order to understand that, we just need to create a vector field, which we can say the velocity is equal to the radius times the rotation rate. So we can find the velocity at any point, at any radius, and we can use special relativity to tell us what effects of relativity are going on. So once again, we can thoroughly understand this type of motion using only special relativity, and general relativity is not required. So let's take a look at gravity on a massive body. Well, we can come up with an acceleration field, and that's simply Newton's law of gravity. And that will tell us about the gravity at any radius, and it's a pretty good approximation of what's going on. But we want to know about the relativistic effects. We need to know why starlight is deflected more at the surface of the sun than would be predicted by Newton's laws. Just as in the other cases, we need a velocity vector field to tell us what's going on with the relativistic effects. So, is there a velocity vector field that will work for a massive body gravity? Well, it turns out there is, and it happens to be escape velocity. If we use escape velocity, we can calculate the rate the clocks will run as you get deeper and deeper into the gravity field or farther and farther away from it, and we can calculate the length contraction effects that are going to happen, the curvature of space-time as you get closer to the center of the object, or if it's a black hole, to the event horizon. So between the acceleration field and the velocity vector field, we can fully understand what's happening in massive body gravity. And this is basically what fluid space theory is all about. So let's take a look at the time dilation formula from special relativity. And we'll take a look at the escape velocity equation. So if we replace v squared, and in this case, if we square v, we get 2gm over r. And if we look at the time dilation formula, we can see that the v squared has been replaced by 2gm over r. So really, when Einstein calculated the deflection, he used gravitational potential, but in order to apply relativity to it, he had to put that potential difference into a form that would work in his equations. And basically, he used escape velocity, although he probably didn't realize it. And if you use escape velocity, it correctly predicts the deflection of starlight at the surface of the sun. I've done the calculation myself, and it works. Now that we understand each of these forms of gravity, and we have a simple method to apply to them, there's no need to use general relativity at all. We can discard it. We can throw it out the window. We don't have to use the complicated math. We don't have to think about Riemann spaces or tensor calculus. We can use an acceleration field and a vector field. Most people won't realize it for quite a while, but Einstein's theory of 1916 has been overthrown. It's rendered irrelevant, and it has no foundation. Einstein may remain on his pedestal for a while, but his pedestal is crumbling, and it's about time. So if you like this video, help me spread the word, show it to a physicist, help them understand what's really going on. And until next time, I'm Hugh Manfield.